stream in. Live. I don't have good hanging spot. Anyway. Yeah, how are we gonna hang that? Yeah, something to hang from, right? All right, we'll get there. We'll figure it out. All right, so in the project for module 3, it's all about like setting up equations of motion and understanding like what equations of motion are and that kind of stuff. So we have, if we have like, give me my pen, there we go. I have like this big old block of aluminum, and it's going to be my pendulum, and it's attached to a string. I can say that, all right, there's a relation between this angle, like how fast the angle is changing, and the angle itself. And what we kind of figured out is like a few different ways. It's like our equation of motion is like the angular acceleration is always proportional to the sine of the angle. So the bigger the angle, the more it's pulling it back to 0. And if acceleration is really high, then velocity is going to be really high. It'll swing right through and then move on to the next thing. So let's say today, what we want to do is say, does this work? Like, did we capture enough physics? We ignored friction, we ignored drag, we ignored relativity, we ignored like particle duality, like wave particle duality, like all these things got ignored so that we could just have a nice one line simple, and we call it the simple pendulum equation. Doesn't mean that it's simple to get there, it's just as simple as it gets without making it more complicated. So if we want to try to measure something and validate this equation, so with real measurements you can validate something. If you're doing like 2 different approaches, usually that's verification. So how do we validate this? What can we measure to validate this result? If we have a pendulum, what do we need to do? What do you think? How would you measure? What would you measure? Yeah. Okay, yeah, first we need to know like how long it is. So we'll figure out how long it is, right? That one's like pretty easy. You heard the joke about the 2 engineers trying to measure the height of a flagpole? No. 2 engineers are like struggling to keep their like measuring tape on the flagpole, and it keeps falling over. And then a woman walks over, takes the flagpole down, measures the length of the flagpole, and then puts it back up and says it's 38 feet and 6 inches. And when she walks away, the 2 engineers go, typical woman. We wanted the height, she gave us the length. Right? Because they're like, so can't accept that someone else can do the job as well. So anyway, we can measure height or length. So I'm 5'9", so now we have a 5'9" pendulum. It's a good start, right? and we'll have to figure out a way to secure it somewhere. I feel like TE is a bad idea. But we know the length. So we can say length is 5'9", right? It is 1 Cooper high, or tall, or long. It's both the same. One length, one value. Cool. Does that, have we validated our equation yet? No, but we can make a prediction now. We can make lots of predictions now, right? What kind of things can we predict with this one equation? What can we do with an equation of motion? Oof, long weekend. Just like completely not coming back. What can we do with it? Nothing. Someone else can do something with it. I'm not doing anything. So it's a differential equation, and we can solve differential equations. We could get like angle as a function of time. So if we know the initial angle, we could say like this is going to be the angle forever. It's always going to start at something, go to something else, come back to that. So I could solve this initial value problem. Theta of 0, let's say it starts at 10 degrees, like a small angle. Theta dot of 0, we'll say that it's moving 0 radians per second. So 10 degrees is going to be 10 over 180 times pi. Pi over 18 radians. So if I solve that, then I end up with this equation that theta of t is pi over 18 times the cosine root g over lt. That one's definitely like some magic here, magic arrow. But I can do some math and figure out, so I'll plug in the initial values, get to this equation that theta of t is cosine root g over L times t. So if I want to say that this equation is real, like that my like physics, my understanding of physics can be applied to reality, what would you want to measure from this equation? What would you measure? Do you want like protractors out? Start measuring angles. Keep track of them. Angles and a timer. T equals 1 second. 0.38 radians. 2 seconds. 0.39578 radians. Something like that. No? Maybe? What's the easiest thing to measure? Angles are not easy to measure. I don't know if you've tried to like make cuts where the angles match up, cuts in wood, actually match the angles. Have you tried that at all? Has anyone done any woodwork or metalworking, tried to match the angles? It's not like rocket science, like you can do it, but it's easy to make mistakes. So it's hard to measure an angle in general. And then if you want angle as a function of time, that can also be hard. So maybe we would want displacement. Like we could take L times theta times cosine and find like how far away. But even displacement now, we need some way of marking off at what time is what position because theta is always changing. It's always a function of time. It keeps changing. So position is always a function of time. What's something that's constant in these? What's a couple of things that are constant? So time keeps changing. What is this thing? That root G over L. The length is the same. Yeah, so we have like same pendulum. Length is the same. What is this? Do you know what this term is called? Omega? Yeah. Angular acceleration, kind of. Yeah. Because a little bit. It's measured in radians per second. But it's a little, yeah, it seems like angular velocity, right? But it's actually like a measure of how far through like a cycle you're getting per second. So like if you go 2 pi cycles, then you've gone through 1 cycle. Like if you have number of cycles per second, what is that called? Frequency? Yeah. Frequency. So this is our natural frequency. Frequency is so much easier to measure than everything else. Displacements, accelerations. I mean, accelerometers, we have them in our phones. We could like attach an accelerometer, but now we have a phone swinging on the pendulum, and we need to like now do data processing on the acceleration, on that accelerometer data. Frequency is always just counting. Just how many times did something happen per second. So we need a timer and then some way of counting. And then we could measure, we could have our own measure of natural frequency. So if our length is 5.9 and G, since I'm using feet, say that it's 32.2 feet per second squared. How many radians per second is what's our natural frequency there? That one's not a trick question. It's just straight up. We got to do division and square rooting. So figure that out, and I'll figure out something here. I feel like we could get away with the ceiling, right? It's not that heavy. As the ceiling comes crashing down. I think there's something up here I can attach to. What? How many knots do I have in this thing? I was trying to just do it without deknotting, but closer. All right, so how fast, what's the natural frequency there? Now, shouldn't bother it. We should be good. What is our natural frequency? How fast is it going to be moving? Or like, how long does one cycle take? One swing? What's that square root of 32.2 over 5.75? 2.37? Oh, I can. And then how do we measure radians with our counting? Sounds a little tougher, right? So we don't measure radians because I can't see radians, but I can see out, back, out. Like I can see one full cycle. So if the pendulum starts here, so 1, goes to here, 2, and then comes back to here, then 3 is like back to state 1. Like I'm going through one full cycle. So that I can measure. So I just need to get that 2.37 radians per second times radians in the denominator. So one full cycle is 2 pi, and one cycle, so 2.37 divided by 2 divided by 3.14. Oh, disappeared. 2.37 divided by 2 divided by 0.14. 0.38. Yeah? I like to put like an F just to remind myself that that is like frequency that's actually measurable and not like natural frequency that's in radians per second. Always do your math in radians per second and then measure stuff in like cycles per second. It's just easier that way. We'll move. Now I'm blocking. Oh wait, but we have with modern technology, right? And we just need to get this guy. Pretty close. It's real time. There we go. So now we need a timer, and then we also have to count, like how long did it take, and then and also how many cycles did we get? How many should we measure? How many cycles? Like how many times should it swing? There's no like wrong answer here. 10? 10 is good. Yeah, 10's a good number. Gives you a nice like average. Some of them you might not care for, but if you get enough, then it's good enough. If we do 10,000, it's a long class. It's just like watching a pendulum slowly put you to sleep, but it would work sooner or later. And I guess don't we have a timer on YouTube or no? No, it doesn't show us the time. Timer? No. Stopwatch. That's what we want, right? So I'll hit start, and then we can start counting how long it takes. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Ten cycles in 26.68 seconds. What is that frequency?
0.37.
What is it?
0.37.
0.37? Is it 0.37?
0.373. I timed it out by 26.8.
Yeah. 0.8? Yeah, I had like 6.8, but yeah, like.
Okay.
But you got 0.37? This is probably pretty close, right?
Yeah.
How accurate is our model? Pretty darn accurate. What's the actual like accuracy? Like, how do we measure accuracy? What was the error in our model versus real life measuring? Yeah. Standard deviation. Well, here we only have like one value each. So standard deviation is 0, and it depends on the definition. If you divide by n-1, then it's actually infinity. That our standard deviation is infinity. But a lot of times it's square root of the mean minus, or sorry, the value minus the mean squared all over n. So standard deviation, that would be good for measuring like precision of the measurement. So if we did this 3 more times and we got like 0.37, 0.38, 0.39, standard deviation would tell us that our measurement is only so precise. And that is a great way of doing precision of a measurement. Yeah.
You just take the experimental divided by the one we calculated.
And divide it by?
Yeah.
Divide it by? So error equals 0.37 over 0.38 equals maybe like 99 point something % wrong. So we have 99% accurate. Yeah. Or no? Are you trying to add something or just like? Oh, sorry. Yeah.
Oh, no, sorry.
99% like accurate. Yeah.
1 minus that number.
1 minus that. Yep. So usually, in general, it doesn't matter what you're comparing. Error is like measured minus predicted. Oop. Or expected minus predicted or something. You just take the two values, subtract them.
The camera's still over the screen.
Yeah, you can't see anything. So it's going to be like measured minus predicted. And if we want to talk about like relative error, then we can do exactly what you were saying, where you divide by that. I would say this one is up to interpretation. Me personally, I think if you actually measure something, that's a true value. There might be errors in how you measured it, like maybe something's wrong with, like maybe I'm not very good at counting, or maybe my timer was not quite accurate, but it's a real result. Like I can't go back and math my way out of the fact that that's what I measured. So to me, the true value of like what the model should predict is whatever I measure. Some people have a different view, like Platonists, where really this is just a representation of the true form of a pendulum, and the true form, and this is just a pendulum with errors associated with it. I don't know. Depends on your philosophy, I guess. But then we end up with exactly what we brought up in the first place, where we said we can take predicted over measured, and it's 1 minus that like 99% kind of value. So our error is only 0.01 cycles per second, and 0.01 divided by 0.37, 2%. Like a 2% error. I mean, that's pretty, or wait, 2%? Is it 2? Anyway, I think it's 2. 0.01 of 37, about 2%. I think that's right. 1 over 37, about 2%. It's pretty good. Do you know where that might have come from? The error? Is it because of drag or friction? Like, is there friction causing something? What would cause 2% error? Measurement, forces that we didn't account for. Yeah.
It could just be like when you stop the timer. How
could be how well I stop the timer. Yep. So one thing we could do is take that 28.68 seconds and give that. We could say, really, this is plus or minus, maybe, I'm going to say I'm like pretty good, say a fifth of a second. Within a fifth of a second, I was able to capture these 10 values. Also, another reason that 10 cycles was better than just like 1 cycle, because I'm still going to be about a fifth of a second accurate, but 1/5 of a second over 40 seconds, or sorry, 30 seconds is not that big a deal. So that 0.2 is not quite like 2% of that 27%, right? 0.2 divided by, say, 27. That accounts for maybe 0.7%. So it could be that, and maybe I'm overestimating how well I can stop the timer, but I think 1/5 of a second is roughly good. Yep.
In our frequency equation, we're just gravity is the driving force
Yep.
of the pendulum. But
Yeah.
when you let go of it, it's possible that you let it a force without noticing it.
That maybe I pushed it. Possible. Yeah. Would that change our frequency though? Would it change natural? Like if we come back to like this equation of like solving this, and it's one of the reasons that like measuring frequencies is that's like how NIST measures time. It's their standardized measurement for time. They know the natural frequency of a cesium atom as it vibrates, and they can measure a number of cycles per second, and that's how we get clocks, and that's how we know what time it is in the day. It's our definition like of the second. So if I added like, if I accidentally said, okay, well, there was an initial speed of 5 radians per second, it would change the amplitudes of stuff, but it would still be the same like frequency of oscillation. But that could happen, right? 5 over root G over L times sine root G over L. So we would end up with like an extra term, but still oscillating, but at a different phase of oscillation. You were like, at least from my thinking, I don't mean to like push you into my one way of thinking. It works pretty well, my brain, and the lessons that I've learned along the way. But you're on the right track, at least of like what I was thinking about, of like, hey, look, we only have these 2 things in there, like G and L. G is probably within 1% accuracy, like 0.01% accuracy. There are technically G changes depending on your, does it change with latitude? It changes on your speed. If you're moving east-west, it'll change by 0.001%, but we don't have to worry about that because we're not on a boat, we're in a plane. So G changes a little bit, but not enough. What about L? You watched me install this pendulum. How accurate do you think 5/9 remained during that operation? You think it's still exactly 5/9? No.
I think we trust you did a great job.
Yeah, I'm not saying I didn't do a great job. I'm saying that during this installation process, errors must have accrued, right? Like every manufacturing process introduces errors. This manufacturing process of installing a pendulum into a cardboard ceiling probably introduced an error. How big do you think that could be? Like an inch? I mean, an inch is not too crazy. I also measured it by like what kids do on the playground, like stand back to back. Like, I'm taller than you. Like, so an inch or 2 is totally within the realm of possibility. So we could say like anywhere from 5/8 to 5/10 is probably about what we're seeing here. Let's see, do I have anything here? So 5 over 12 times divided by 2 divided by so I get anywhere from like 0.38 to 0.37. So that natural frequency is kind of like 0.37 plus minus 0.05. Which is our, yeah, more than, yeah. It's bigger than our like measurement error, like our measured versus predicted. So even if we had like better measurement tools, at least unless we can get the length kind of definitely at 5.9, then that's going to be our biggest contributor to error. It's like how well can we measure measure the length of that pendulum. Anyway, just a quick. And now, where did I find? So up on, oh yeah, in the stairwell. That's what we can do. So we can go into the stairwell, and I'll bring the pendulum down the middle of the stairwell, and then we can try to measure the time, and then we'll do the opposite of like how long is that pendulum based on how, well, you can do that on your own, but like figure out, we're gonna make the pendulum super long and see what happens to time period. Because bigger is better, right? Need something bigger. And then I can't really record that, so sorry if you're watching online. We'll go out into like this hallway, and I'll go up the stairs, and I should be able to like unravel it as I go up. All right, thanks for joining.